recording. Okay, so today is the 10th of March. We're going to continue to work through lecture set number 4 today. So up till this point in lecture set number 4, we have done two major things. We have defined the ratio estimator, and we have utilized the ratio estimator to estimate a population ratio, which is essentially a quantity that compares the rate of, well, I guess we could say it compares the rate of change in one variable to the rate of change in another variable. And we have also used the ratio estimator to estimate the population average and the population total. And those are the traditional types of exercises that we have been studying in this course. So our main focus again has been on sampling structure and then how we can compute estimates coming out of a sampling structure. After we studied ratio estimation, we noted that one of the, I suppose you could look at it as a drawback of the approach, was the fact that the ratio estimator requires that there's a linear relationship that goes through the origin for the problem that you are studying. So if you have a strong linear correlation between your variable of interest and your auxiliary variable, but that linear relationship does not go through the origin, you would require a different type of estimation. So we introduced, or we discussed, the regression estimation approach, which is very similar to the ratio estimation approach, with the only difference being that you're accounting for the y-intercept of the model that would relate your variable of interest to your auxiliary variable. In both cases, we studied the properties of the estimators. So we showed that we have approximately unbiased estimators, and we derived expressions for the variance of those estimators. We utilize those estimators and the variance of that estimator in the usual way. So we would construct a point estimate, and then we would bound that point estimate using a 95% confidence interval. An example of such interval is actually shown on the slide we're starting at today. You can see here that we have a 95% confidence interval for the population total in this particular illustration. Okay, so just quickly as a recap, we've seen ratio estimation, regression estimation. Regression estimation is effective when both x and y are continuous, so we require two continuous variables. We require some knowledge of the study beforehand, but not in the same sense as with the ratio estimation approach, because with the ratio estimation approach, we actually require that we knew the mean of the auxiliary variable for the entire population that we were studying. In both cases, we require there to be a linear relationship. And in both cases, the tighter that relationship, so the higher the correlation, the better the resulting estimates are going to be. Okay, so there is one other estimate or estimation procedure that we are going to talk about in this lecture set in the context of simple random sampling. So as a reminder, all of the illustrations that we have seen for ratio estimation and regression estimation have come from estimates that were collected via simple random sampling. So difference estimation in the context that we are going to study it is also resulting from a simple random sample. Now the major difference, or yeah, I guess we can say it this way. The big difference between difference estimation, regression estimation, and ratio estimation is that you use ratio estimation when you have a linear relationship that passes through the origin. Okay. Regression estimation, as we mentioned before, so use for linear relationship doesn't have to pass through origin. Okay. And then the last one is what we're calling difference estimation. Difference estimation, like ratio estimation and like regression estimation, requires that there's a linear relationship between X and Y. So between the variable of interest, well, between the auxiliary variable and the variable of interest. The differences, though, as you can see, for example, on the slide here, we have, it doesn't actually require that we model the linear relationship. So we expect it to exist, but we don't need to utilize the model. And then the big difference is that we use difference estimation. So we have a linear relationship, but both variables are measured on the same scale. So it is a function of data type in that case. So we can say here, so use for linear relationship variables on same scale. So it's a very small distinction between this approach and the regression estimation approach. So that distinction, again, is simply that if we are measuring two variables that are on the same scale, so this is kind of the same idea as when you think about paired data. So you have a set of observations, and each observation is contributing two measurements on the same, or for the same variable. So the classic example of this would be you have, say, 20 people that were collected via a simple random sample, and you measure their weights in the morning and you measure their weights in the evening, right? So this creates what we refer to as a naturally paired structure. We consider these measurements to be dependent measurements because they're coming from the same individual, but we want to compare those measurements to one another. So our difference estimation approach is a tool that we could utilize to compute the mean of, say, the weight in the evening by incorporating the weight in the morning and the fact that we expect there to be a linear relationship between those two variables. Okay, so our estimates for the mean of Y, or for the mean of the variable of interest, using difference estimation are given on slide 47. Okay, so we have mu tilde for the difference, or mu tilde via the difference estimator, is equal to mu x plus, this would be mu tilde d. Okay. And then here we can see mu tilde d is simply the difference between mu y and mu x. Okay. The variance of mu tilde d is given by the second expression. So we have our FPC multiplied by 1 over n. So those are familiar leading constants for any of our variance estimates that we have studied in the case of regression and ratio estimation. And then we have this novel term, if you will, and we can think of this thing as simply an estimate of the variance of the squared differences, or of the differences in this case. And here we have a DI term, right? So this is YI minus XI for each observation in the data set. Okay, so to illustrate the difference estimation approach, we'll use, I guess if you've seen my lecture slides before, this is a fairly classic example that I utilize a lot. In this illustration, we have a taxi company is trying to decide whether the use of radial tires instead of regular belted tires improves fuel economy. 16 cars are equipped with radial tires and driven over a prescribed test course. Without changing drivers, the same cars are then equipped with the regular belted tires and are once again driven over the test course. The gasoline consumption is given in the table below. Okay, so we have 16 observations. We're going to assume that these are 16 randomly selected cars, so an SRS of size 16. We have fuel economy measurements for each set of tires that are equipped to the car. And we're using the same car across each test lap. So we're going to assume that there's a dependence between each of the measurements on the observation under consideration. Further, we're in a situation where the measurements that are being returned from each observation are in the same or have the same units. So they are fuel consumption measurements. So for example, on observation 1 for the radial tire, you have 4.2 kilometers per liter. Observation 1 for the belted tire, you have 4.1 kilometers per liter. Okay, so this is a situation where we have measurements that are occurring on the same scale. Now on the next slide, just before we get into the calculations and a little more discussion, we have a scatter plot of the belted tire measurements versus the radial tire measurements. Okay. Oh, come on. All right. So the purpose of the scatter plot, again, is to show that there is, in fact, a linear relationship between the measurements coming from each observation. So we have linear relationship, measurements on same scale. Okay, so all three approaches, again, ratio, regression, and difference estimation, have the same requirement, which is the variables are linearly correlated with one another. And we can see from the scatter plot here that we do have evidence of this correlation. Now we can also, but in this particular illustration, we can see that each measurement is on the same scale. So the difference estimation approach is typically utilized when you're in a situation where you have the values being given on the same scale, which is what we're working with here. Okay, now in looking at this, okay, actually no, it's fine. So we have, suppose this sample is taken from a new company that only has a total of 35 cabs. Use the radial tire consumption to predict mu y when mu x is equal to 6.5. Okay, so we're going to be predicting the belted tire consumption in this case, based off of the plot that we're using and based off the language in the question. All right. So to estimate mu y, we can use difference estimation. So we're going to have mu tilde, well, I guess it'll be mu hat diff in this case because we're going to start plugging in. So we're going to have mu hat diff is equal to mu x plus mu hat d. Okay. So this is going to be mu x plus mu hat y minus mu hat x. Okay, so this is going to be 6.5 plus, and then what we'll have is 5.7 minus 5.83125, which is equal to 6.36. Okay, so we have two values here, the 5.7 and the 5.83125. So these are respectively the means of the belted tire fuel consumption from the sample and the mean of the radial tire fuel consumption from the belted sample. So if we go back to our previous slide, for example, what we're saying here is that mu hat y is equal to the sum from I and S of the yi multiplied by 1 over n. So that's going to be, in this case, 1 over 16 multiplied by 4.1 plus 4.9 plus 6.2 all the way up to the last, well, across all 16 measurements for the belted tires. Okay. So there's simply just the sample means for each measurement respectively. Okay, and then mu hat x would be the same idea. All right, so those two calculations just came from finding the means of each variable. Okay, so now what we have to do is find the differences or the variance of mu tilde diff. So the way that this is going to work, we're going to have the estimate of the variance of mu tilde diff is equal to 1 minus little n over capital N multiplied by 1 over n, which is multiplied by, well, I suppose we can write it like this, which is multiplied by sigma hat d over little n. Okay, so sigma hat d is going to be equal to 1 over n minus 1 multiplied by the sum from I and S of each di minus mu hat d squared. Okay, so the di, again, are the yi minus the xi for each observation in the data set. Okay, so for example, going back here, we can show, for example, that d1 is equal to 4.1 minus 4.2, which is negative 0.1. Right, d2 would be 4.9 minus 4.7, which is 0.2. D3 would be negative 0.4. D4 would be negative 0.1, all the way up to D16, which would be negative 0.1. Okay, so there's simply the differences between each pair of observations in the data set. So our variance calculation here is actually just the variance of these differences, except that we're taking it around mu hat d, which should work out to be the same thing. Yeah, so but we're taking it around mu hat d, which should be very similar to the mean of the di directly. But that's something that we could actually check to see if there is a little bit of a difference. But I don't expect that there would be. Okay, so then this is going to give us 1 over 15. And then if we take this term here, we'll have 0.774375. All right. Okay, and then that is going to be equal to 0.051625, which means that our variance of mu tilde diff will be equal to 1 minus 16 over 35 multiplied by 0.051625 divided by 16, which is 0.00175. Okay, so then our 95% CI for mu y will be 6.36875 plus or minus 1.96 multiplied by the square root of 0.00175. And that should give us something in the area of 6.33 to 6.41. So hopefully you agree that for the most part, these calculations are very similar to what we have seen before, at least maybe not in 350, but across different courses. So there's nothing overly complicated about how we're getting to these estimates. But I mean, it is fair to say that they are fairly taxing in some sense, given that we have to compute all the differences and find the variances and whatnot. Any questions? So we're using difference estimation to find an estimate for the mean of the variable of interest. So the confidence interval would be for the mean of the belted tire measurement, which is actually the mean of what we are calling y. So difference estimation leads to an estimate for the mean of y. And the intervals are always constructed about our estimate for the population variable. Does that make sense? So another way to think about it is so we want to estimate mu y. So across all of the different approaches that we've talked about, we want to get an estimate for mu y. So one way to do this is mu tilde y, which is the SRS estimate, so the direct estimate. Another way to do this would be mu tilde ratio, but this is still estimating these are both estimating the same quantity. Then we have mu tilde regression, and now we have mu tilde diff. So we have actually we now have four different approaches based off of a simple random sample. Yeah, exactly, to estimate the same quantity. Yeah, so what you wrote there is exactly correct. Mu diff gives us an estimate of mu y, where y is just a placeholder to say variable of interest. So that's basically the same as saying we want to estimate the mean of the variable that we are interested in, and then we're just using y to represent the variable that we are interested in. So actually, that's a really good question to set up the next part. So from that question, we have now this little breakdown here that's basically showing us that from simple random sampling, we have 4 different ways of measuring the same quantity. Which measurement is going to be the best? Okay, and I should say best in quotations. Well, to define the best measurement, our strategy is to compare the variation of those estimators. So this is actually the last part of question 4 on assignment number 3, which is asking you to compare the variation of, I think it's the regression estimator to the SRS estimator, but I don't remember exactly, but it's something along those lines. So this comparison of variances leads to a measurement that we can refer to as the relative efficiency. So the relative efficiency is a value that takes the variance of one estimate and divides by the variance of another estimate. So we can use the relative efficiency to basically make a statement about which of the 4 estimates that we have considered is the better one based off of the value that is returned via the division of these variances. Now, the relative efficiency itself is a somewhat fancy way of explaining how this comparison is going to work, because from a logical point of view, you can see directly from the formula on slide 50 that if we're dividing 2 variances by one another, all of our interpretations are simply going to break down to a comparison about the value of 1. So what I mean by that is if I have the variance of, say, mu hat SRS, mu tilde SRS, and I have the variance of mu tilde ratio, and I divide the variance of mu tilde SRS by the variance of mu tilde ratio. If that value is equal to 1, that is saying that those 2 estimators are acting in the same way. So they're explaining, or they are as precise, each variable, or they both share the same amount of precision, if you will. So our relative efficiency estimator, while we can talk about some of the properties that we will expect to observe from it, based off of its construction, it's simply just a comparison where we are using 1 to mean equivalent. So then you have above 1 or less than 1 as being, or we have values above 1 or values less than 1 that would explain which estimator is acting better in the particular situation or is more efficient. All right, so we have some requirements when we are using our relative efficiency estimator. The first requirement is that both of the estimators are unbiased or have very small bias. Now, this isn't exactly the case for the estimators that we are talking about. So for example, for the ratio estimator, we actually show that this is approximately unbiased, but the estimator itself is a biased estimator. But if we have a strong linear relationship that runs through the origin, that bias is small enough that we could ignore it for the purposes of using the relative efficiency approach. Similarly, with the regression estimator, again, we have that it is approximately unbiased, but we require that it has a strong, or that there is a linear correlation between X and Y for it to be, to have a negligible bias. Okay, so these are important considerations when utilizing the relative efficiency to compare with, I don't know why I wrote this sideways, mu tilde ratio and mu tilde regression. Okay, so these are 2 points that we want to keep in mind. With the difference estimator, we're actually in a good situation because we can show that this is always unbiased in simple random sampling schemes. Okay, the second requirement is that the estimators are compared using the same sample size. Now this should be a fairly obvious requirement since n going to infinity results in variance of estimator, or I'll just write this as mu tilde, going to 0, right? So it wouldn't be a fair comparison if we took ratio estimation, where the estimator of mu was computed using, say, a sample size of 200, and we compared that to a regression estimator approach, where the estimator was computed using a sample size of 10. Even though in that situation, the regression estimator might be more appropriate because the line doesn't pass through the origin, for example, by using a larger sample size, you're naturally going to observe a decrease in the variance of the estimator. So this is going to make the ratio estimator look more appropriate, even though in reality, the regression estimator might actually be the better choice for that particular problem. Okay. So going back to one of our original discussions on the idea of being the best. So we define our estimators as being ideal when they are unbiased and they have minimum variance. So the relative efficiency is really just an extension of this idea. So we are saying that we want, or we already have established that we want our estimator to have the smallest possible variance. The smaller the variance means that we can observe, or we have a higher precision. So when we compare, well, this is really just a result of what I said before, but when we compare our estimates, we're saying that the estimate with the smaller variance is the more precise estimate, given that they're both unbiased. So the relative efficiency is essentially taking into account this definition. Okay, so here we go. So when we use the relative efficiency, and this would follow naturally from the definition of the relative efficiency calculation. So if we have, for example, our E of E1 over E2, this is the variance of E2 divided by the variance of E1. So if the relative efficiency is greater than 1, this is saying that the variance of E2 is larger than the variance of E1, which means that E1 is technically the better estimator. If the relative efficiency is equal to 1, this is saying that both E2 and E1 have the same variance and therefore are equally as precise. If the relative efficiency is less than E1, then E2 is smaller than E1, which means that E2 is better. Okay, one of the things that's worth taking into consideration here, if you understand the underlying purpose of the comparison, which is basically just to compare the estimates of the variance of the estimator, it really doesn't matter how you set up the relative efficiency calculation. This again is sort of a fancy way of expressing what is a very natural idea. So for example, if you wanted to compare two variations and you divided E1 by E2, or you did the opposite and divided E2 by E1. As long as you understand what it means when that expression has a value greater than 1, less than 1, or equal to 1, it doesn't make a difference which order you divide in. So what's more important here is simply recognizing that when the relative efficiency is equal to 1, or when the ratio of the variances of the estimators is equal to 1, it doesn't make a difference what order you divide in. When the ratio of the variances is larger than 1, that implies that whichever variance is in the numerator has a higher value. When the ratio of the variances is less than 1, that implies that whichever variance is in the denominator is the lower value. Okay? But for those of us that like hard rules or following structure, that's what the relative efficiency is for. Okay, Now, there are a few other considerations to take into account when we're using the relative efficiency. For example, an RE greater than 1 does not necessarily mean that the true variance of the estimator is larger than the true estimator of the variance for E2 is larger than the true estimator of the variance for E1. As we know in many practical applications, if we collect a sample that, say, is a part of the tail of, or is the majority of the sample comes from the tail of the distribution that we are studying, we might observe a situation where we have, where we can make an incorrect result in the context of hypothesis testing. We can have that same issue when we're comparing the variances. So a lot of the time, this really depends on where we are collecting from. So ideally, as in any situation, we can repeatedly sample from the same population in order to have multiple estimates of the relative efficiency, the variation of our estimates, et cetera, that we can utilize across, or that we can use to compare and observe how the value behaves across repeated sampling. And actually, that would lead to another point, which is potentially a way to bound the relative efficiency using, for example, a confidence interval, so that we can make a general statement about whether or not that value or that interval contains 1 or does not contain 1. Okay. So we're going to look at some different situations now. We're going to talk about some breakdowns. We're going to look at general comparisons as well, where we just use the variances. In all situations, again, the relative efficiency is simply a comparison of the variances of the estimators. A lot of the estimators that we have discussed in the class so far, they share similar forms. So for example, they all have an FPC. They usually have a 1 over n term, a 1 over little n term. And then the differences typically lie in the variance estimate that's being plugged into that particular quantity. So for example, here, where we're comparing the SRS estimator to the ratio estimator. So we have the variance of mu tilde y divided by the variance of mu tilde r. Okay, so this here is our SRS estimator, and this here is the ratio estimator. Now going back to the point that I was making before, so as a reminder, this first variance term looks like this, okay, where you have sigma squared y, which is simply the variance of the observed value of interest. And then the ratio estimator has a similar form. So we have this leading 1 over mu x squared term, and then we have sigma hat ratio over little n. So you can see that there's actually quite a few terms that cancel out here. And really the comparison of the variances in most situations just boils down to a comparison of the sigma hat terms that exist within each of the different estimators that we are working with. Because the FPCs are going to cancel out, the 1 over n term is going to cancel out. In this case, we have the mu x squared. But you can see that if we do not know mu x squared, we actually can get a simplification of this particular, well, I don't know if you'd call it a simplification, but you can get an alternative expression for the relative efficiency of the ratio estimator to the SRS estimator, which is given in equation 7. So here we have sigma squared y, and then on the bottom, we have sigma squared y plus theta hat squared, which is our estimate of the ratio, multiplied by sigma squared x minus 2 times theta times the correlation between y and x, multiplied by the standard deviations of x and y respectively. So in this particular situation, if we don't know mu x, we can still compare the efficiencies of the two variations. Though that being said, to compute the variance in a general situation, we would have to have mu hat x, but it's worth pointing out that we can write the comparison this way. Okay, so then we can also show that the SRS estimator will be less efficient. So notice here we have greater than 1. So again, what this is implying is that the variance of mu tilde y is greater than the variance of mu tilde r. So this is going to be true. So basically, the ratio estimator is going to be the better estimator in the following situation. So for example, obviously when the numerator is greater than the denominator, as per the first point, that's a lot of insight there. But also when, for example, 2 times the correlation, and these should be, sorry, sigmas. Okay, when 2 times the correlation multiplied by the standard deviations exceeds theta squared times sigma squared x, or when 2 times the correlation times the standard deviations exceeds, oh, this is the same thing. Oh, times theta times sigma squared x is, sorry, when 2 times the correlation times the standard deviations exceeds theta times sigma squared x, but this assumes that theta is greater than 0. Or in the situation where the correlation exceeds a ratio of the standard deviations multiplied by theta hat over 2. Okay, so let's look at some actual illustrations here. So we want to compare, in this example, we're going to compare the relative efficiency of mu tilde ratio to mu tilde y. So this is the ratio estimate of mu y to the SRS estimate of mu y. Okay, so in part 1A, or we have the following data set. Sorry, so we have 12 observations here. We have the square foot basal area of each tree, and then we have the volume of each tree. We're interested in the volume. Okay, so this is going to be our variable of interest. Okay, so we're going to compute the relative efficiency of the ratio estimation to the simple random sampling estimator when estimating the mean and estimating the total. Okay, so in 1A, we have the relative efficiency of mu tilde, I'll just call it ratio, over mu tilde y. So this is going to be the variance of mu tilde y divided by the variance of mu tilde ratio. Okay, so we have the following sets of summary statistics here. So we can see essentially that what this is pointing us towards is using the one of the simplified expressions for this particular comparison. So here we're going to have sigma. So we're going to have sigma hat squared y plus theta squared sigma squared x minus 2 times theta hat times rho hat times sigma x times sigma y. And then on the top here, we'll have sigma hat y. Okay, now for the most part, we're just going to be plugging in here. So this is a fairly straightforward calculation. You can see that we have the majority of the required component. We have all of the required components above. To get sigma x and to get sigma y, we'd have to take the square root of sigma hat or sigma squared x and sigma squared y. Theta here is going to be the ratio of mu hat y to mu hat x. Okay, so make a note. So we have theta hat is equal to mu hat y divided by mu hat x. And then each standard deviation is just going to be the square root of the estimate. So given those notes, we should be able to show fairly easily that this is equal to 15.356. 7. So you can see in this case, we have a relative efficiency or a ratio of these variances that is much larger than 1. So this would imply that the variance for the ratio estimation approach is far superior to the ratio estimation procedure is superior or way more precise than the SRS estimation procedure. So ratio estimation. Okay. And again, even without setting it up as an RE comparison, if we just compare the ratio of the variances, regardless of the order you do it in, you'll end up at the same result. So if you had the expressions flipped such that what I have in the numerator is now in your denominator, this would just be a value that's much less than 1. So the conclusion would be the same. As long as you can recognize that 1 means the value of 1 is a quality, as long as you can recognize the value of 1 as a quality, then if the number is greater than 1, that implies that the numerator variance is larger. If the number is less than 1, that implies that the numerator variance is smaller. Okay, in part B, we're asked to do the relative efficiency for the total. Now this is kind of a cool result. It might be expected for some of you, but if we do the relative efficiencies for the total, we end up with the following. So if we have tau hat ratio compared to, well, I guess these would be tildes, right? Compared to tau tilde y. So this is going to be the estimate of the variance of tau tilde y divided by the estimate of the variance for tau tilde ratio. Okay, so this is going to be n squared multiplied by the variance of mu tilde y divided by n squared multiplied by the variance of tau tilde y. Sorry, mu tilde y, or mu tilde ratio. Okay, and then what we can see from this very simply is that we get cancellation here of the n squares, right? And that might be what you expected to observe. Okay, so that means that this is actually the exact same relative efficiency as in the case of the mean estimator. So those values are equivalent. So this again is going to be 15.356.7. So the relative efficiency of mu tilde ratio to mu tilde y is equivalent to that of tau tilde ratio to tau tilde y. Okay, so I guess that brings us to the end of today's material. So we'll look at a few more examples of relative efficiency estimation on Friday. We're also going to talk about ratio estimation in the context of stratification. So how ratio estimation would be utilized if we stratified our population. And then after that, we'll start a new unit, which will be on cluster sampling. So as always, if you guys have any questions, please let me know. And otherwise, I will talk to you on Friday morning.